Um, my name is Matthew Kahle. I'm a professor at Ohio State University. I've been here, this is my 10th year, I guess. Before this, I had postdoc positions at Stanford and at the Institute for Advanced Study in Princeton. And I did my PhD at the University of Washington in Seattle. In a way, I think I knew I wanted to be a mathematician when I was a little kid, although I didn't even really know what mathematics was at that time. When I think of myself as a young mathematician, I think about when I was maybe 8 or 9 years old, the Rubik's Cube coming on the scene in a big way, and from the first time I saw it, I was hypnotized by it, and then I was obsessed with it as a child. So to me, the Rubik's Cube was a puzzle, a fun thing to try to figure out or to try to learn how to do, and then it's much later that I learned that it actually has something mathematical to it, that we can describe the structure of the Rubik's Cube using mathematics like combinatorics or group theory. As a kid, I could feel confidence if I got the right answer on a math question. I knew that it was the right answer because I could check, maybe do it a different way, and if I got the same answer, that was reassuring. And then sometimes writing, an essay for an English class, I didn't really know if I was doing it right, or what they expected, what they wanted me to do. So somehow I found math, maybe more comforting, or I felt more secure that if I could figure it out, if I knew the answer, then I could be sure that the answer was right. Research as a mathematician is pencil and paper, drawing pictures, and maybe doing some computations. But I think of it also as a very collaborative endeavor, and so research might be getting together with someone and trying to figure something out together. Could be sitting in an office and taking turns going to the chalkboard. It could be sitting in a coffee shop and drawing together on a notebook. And these days it might be meeting with somebody by Skype and taking turns sharing our screen, drawing pictures on our tablets. So it's one maybe advantage of mathematics versus other sciences is that we don't really need much in the way of apparatus, and we can do research in principle anywhere. Another aspect of it, though, for me, and I think for many mathematicians these days, is there is an experimental aspect to it sometimes, or a computational aspect, where the computations get big enough that you can't do it by hand anymore. It's not something you can do on scratch paper, but on the other hand, maybe it can be done with some clever software. And so research could be writing code to try to test our conjectures, to try to test our intuition, or to compute the next example in a sequence that you can't do by hand. So I think more and more computers are part of research, even in the most theoretical branches of mathematics. And not only do they help us, sort of sharpen our conjectures and intuition, sometimes they help us prove theorems. Sometimes they help us even make new conjectures as to what's really going on. I feel like I work in the intersection of different areas of mathematics. At heart, though, I feel like I'm a topologist, so I study topological spaces, which can be it's really the study of shape, although the shapes that we're studying can be quite complicated, and they could be, for example, very high dimensional. More specifically, I work in stochastic topology, which is the study of random topological spaces. So what are the properties of random shapes? And then lately I've been very interested in sort of topological statistical mechanics, which is the shapes that we're studying are configuration spaces, spaces that record all possible configurations, somehow encode it all in one space. So it can be hard to visualize high-dimensional shapes, but fortunately, over the last 100 years or so, mathematicians have developed a number of techniques for studying them anyway. So one of our main tools in algebraic topology, for example, is homology. And homology is, something that you can compute about a space, and there's many techniques. So by now, mathematicians are very good at computing homology of various spaces, even fairly complicated ones. And the analogy that I sometimes thought of is that, astronomers can see some galaxies or stars that are very far away and are not visible to the naked eye at all with radio telescopes, for example. And these stars might not even be in the visible part of the spectrum, and they're very far away. But they can see them with a radio telescope, and then they can start to measure the star's properties. How far away is the star? How big is it? What kind of star, and the classification. So for us, homology is like that in algebraic topology. It's our radio telescope. Even though space might be very complicated, or it might be very high dimensional, homology tells us something about it. So one way we think of homology is how many holes does a space have. So it's telling us something about the shape. This was a very collaborative project. I worked on it with Hannah Alpert, Yuli Bauer, Bob McPherson, and Kelly Spinlove. And the five of us together studied the configuration spaces of hard squares in a square. So what we're looking at is a system where you just have kind of a square or rectangular board, and that's your sort of universe. And the atoms there are just little squares, and they have to keep their sides parallel to the sides of the big square that they live inside. So this looks a little bit like the 15 puzzle that we played with when we were kids, where it's a sliding block puzzle, sort of a two-dimensional version of the Rubik's Cube. It's of interest to physicists because it's one of the simplest models of matter that you can imagine. Your atoms are just little squares, but it's somehow complicated enough or rich enough that they think it goes through something like a liquid-solid phase transition. We know that liquid changes to solid if you get it cold enough, but in some sense we don't really know why that happens, or why it happens so ubiquitously for many different materials. So I would say we kind of understand the geometry in some ways of a solid. It's something like a crystal, and if you look at the atoms, they're arranged in a very nice kind of lattice arrangement. It's very predictable. And in some ways we understand the geometry of like a gas, that the atoms are kind of random and spaced out. But what's happening inside a liquid is much more subtle and mysterious. So what they run kind of computational experiments with this sort of system, and there's some reason to think that once the squares take up the little squares take up a certain percentage of the area, that the behavior of the system changes, and that the squares sort of start to lock up, and it's like freezing. That's the analogy that they make. But this is what the physicists say from their computational experiments, and there's been very little known about it mathematically. And we made enough headway on this problem that we start to see something that looks like a phase portrait. One of the figures in our paper is we have two different axes, and one of them is the volume fraction, or what percentage of the area do the little squares take up in the big square. And then the other axis is more abstract. It's something like, what dimension of homology are we looking at? So you could be looking for one-dimensional holes in your high-dimensional space, or you could be looking for two-dimensional holes or higher. But we put it on two axes. And the analogy that we're working with here is that this is something like pressure on one axis and temperature or entropy on the other axis. And that we see these phase portraits for water where, as you vary the temperature and pressure, you go through different states. And we have some preliminary results seeing that you go through different sort of topological states as you vary these parameters. And we're able to show that, outside of this zone, there's certain behavior, and inside of this slightly smaller zone, there's this other kind of behavior, and that they're really qualitatively different. A configuration space is a space or a shape that sort of encodes all possible arrangements of the pieces. With the 15 puzzle, for example, there's only, so let's think about all possible positions, and there's quite a few. If you let's say you could put the squares anywhere, they're really mixed up. So combinatorics would tell us that there's essentially something like 16 factorial different positions. That's 16 times 15 times 14. So this is some huge number of possible ways to arrange all the pieces. So the configuration space is a shape where every point of the shape represents one possible configuration. So already for the 15 puzzle, this is a huge complicated shape. So a couple things about the homology of this shape. Even for the 15 puzzle, it turns out to be pretty interesting. So one thing that homology can measure is whether your space is connected or disconnected. And it turns out in some sense, the 15 puzzle has a disconnected configuration space. You can't actually get from any configuration to any other configuration. And this is a famous fact about it. That's been known for 150 years. So imagine just switching the 14 and 15, like like people used to peel stickers off their Rubik's Cube to try to cheat and solve it. With the 15 puzzle, just imagine taking the 14 and 15 squares out and switching them. Well, now if you try to slide the pieces around legally within the grid, you can't get back to the starting configuration where the 14 and 15 are switched. So it turns out homology can detect this, that the configuration space is disconnected, and there's two disconnected components. So now try putting the squares in any possible configuration, arrange them however you like, mix them up as much as you want, and there's only two configurations. So you'll either be able to solve the puzzle to the original configuration where they're all in order, 1 to 15, or you'll be able to rearrange them so that you get to the configuration where 14 and 15 are switched, but everything else is in the right order. So there's two connected configurations. But if you go one step up in homology, H1, the first homology group, it lets you see how many holes there are in the configuration space for the 15 puzzle, and there's a lot. There's sort of, many millions of holes. And these sort of represent configurations that you can't get to because you can't move the blocks through each other. So we said there's something like 16 factorial possible configurations, that the squares could be in. But that's only if they're really on their home squares and every square is perfectly centered on a grid point. But to slide from one to another, you have to go through some intermediate configurations where a square is, halfway between, or, sliding. So there are some other configurations there that connect these. And so the shape of the configuration space is really quite complicated because it encodes all of those possible configurations, and that's what we find. If we compute homology of it, is that the homology is wild. That there's there's only two connected components, but the next homology group is wild in the sense that there's lots and lots of holes. That so even though it's been known for I think 150 years that there's two connected components of this configuration space, the higher homology, I think we're just getting the first glimpses of that. I think a phase transition is like a qualitative change in the behavior of your system as you vary your parameters. So here our parameters are just you vary the number of squares you have in your grid, or especially you vary the sizes of the squares. You can make the squares bigger and smaller, say. So maybe it's more natural, physically, to say that the parameter is varying the size of the grid. You can sort of squeeze it in, the sides of the container, or you can loosen it and make the container a little bit bigger. So that's something like pressure on your system. If you squeeze in the sides of the container, you're increasing the pressure. So the kind of phase transition that we see is something like a shift in the topology of the shape. It's as if you make your squares a little bit bigger, and all of a sudden the shape of all possible configurations has millions of holes in it. And what's happened is that because the squares got a little bit bigger, there's areas that are no longer, there's regions that are no longer accessible. You can't put the squares where they were before because they're a little too big now, and to try to put them there would result in overlap. So all of a sudden holes have appeared, but it's not just like one big hole. There's many millions of holes all spread out throughout the space. So somehow we can detect that with the tools of algebraic topology. That's somehow what I imagine it looking like, is that you had something that looked maybe sort of regular shape, but then all of a sudden you vary your parameters a little bit and it looks like a sponge or Swiss cheese or something that just has lots of holes going through it in every possible direction. And there's all these holes that are representing inaccessible regions in your configuration space. So in a gas, the squares would be able to sort of bounce around freely and wouldn't have much obstruction. Occasionally they would bump into each other, but not very often. But then in a liquid, they're kind of starting to bump up against each other and things are getting complicated. And we think it's possible that this configuration space, the shape changing qualitatively, is telling you something like that about why the behavior of the system is changing. And I should say, by the way, it's exciting that it may be that topology is refined enough, it's somehow complicated enough, the topology of these shapes, that we can see something like a phase transition in a system with only 5 or 6 particles. So I had an older paper several years ago. I collaborated with a material scientist, Jeremy Mason, and he and I did some computational experiments to try to get a glimpse of the topology of configuration space for only 5 particles in a box, and this time the particles were disks instead of squares, and the picture we got was much rougher than the more refined picture that we got recently with hard squares. We didn't really have theorems in this paper. We just had sort of experiments to try to get a glimpse, and we also saw some evidence that the shape of the space is very complicated and changing, and that there could be some phase transitions. So we sent this to a physics journal, and one of our reviewers for the physics journal said, "This is very nice and it's very pretty mathematically, but I'm not sure if it's physically interesting, because I don't believe that you could have a phase transition for a system with only 5 particles. That doesn't make sense from a physics point of view." But so the editor asked us to make revisions and to address the concerns of our reviewers, and Jeremy dug deeper into the physics literature, and we were a little bit surprised to discover that there were hints, even in the late 1960s, in the physics literature, that a system could undergo a phase transition with maybe only 20 or 30 particles or something like that. So where the traditional point of view of statistical physics or statistical mechanics would be you need millions of particles. So millions of particles is way out of reach for any of our computations or experiments. It's exciting that we can do very careful, very precise experiments with just 5 or 6 particles nowadays, and that already we're seeing that if we're studying the topology of these shapes, it's rich enough, it's complex enough that we can see something that looks like a phase transition, even for a small, relatively simple system. The topology seems to capture something's happening. This is a good example of a project where we used computational and experimental methods. So these configuration spaces are quite complicated shapes, and we were only able to compute the first 1 or 2 small examples by hand. But there's a tool in our paper, a mathematical tool that we developed, which is that there's a cell complex that is a model for the configuration space. And if anything you might want to know topologically about the configuration space, you can understand by understanding the cell complex. And so the advantage of the cell complex is that it's something that's finite and that you can actually feed to a computer. So that's the good news. The bad news is that it's still quite large and complicated. So we gave several examples of this to a computer, and for example in our paper we were able to get up to maybe 6 particles, and basically any size grid, but imagine like 6 squares and a 4x4 or 5x5 grid. That's the good news is we were able to compute the homology exactly, and the bad news is that's about as big as we were able to go, because by this point the cell complex that we're looking at has many millions of cells, tens of millions of cells, and it's sort of at the limit of what we're able to compute. So it's possible that one day we'll be able to compute bigger examples if computers are faster and we have more memory and so on. But maybe a more promising idea is if we understand the mathematics better, we might be able to write down a smaller, somewhat simpler cell complex that still captures the topology, and then we're able to compute bigger examples. But what was amazing to us is that even just going up to 6 squares, so you know, again, the metaphor or the analogy is that these are like little atoms. So we just have a little system with just 6 atoms, and the atoms are the simplest thing you could imagine. They're just squares. And the only force is a repulsive force where they're not allowed to overlap. So they're called hard squares. Even for a system that simple with only 6 atoms, and the atoms are just 2-dimensional little squares that can't overlap, we see qualitative change in the behavior of the so the topology of the configuration space changes. The shapes change drastically as we vary the parameters, and we're able to see, even for such a small number of parameters, what we call a phase transition. And so we did a lot of work by hand also, proved several theorems in our paper, and then kind of looking at our experiments and looking at the theorems that we were able to prove, we made some conjectures about what we think is really going on. But the conjectures, I think, wouldn't have been as convincing, and I think we wouldn't have even come up with the same conjectures. They wouldn't have been as refined if we hadn't had the computer experiments. So in our paper, we include, you know, our theorems along with proofs, and that's sort of the part that looks like a traditional math paper. But then there's an appendix at the end that with tables where we compute all our small examples. So anyone else can kind of look at the results of our experiments and see if they notice any other patterns, have any other conjectures that they come up with themselves, or if they want to try to compute it themselves, they can check our results, or, you know, make sure that they're getting the right answers with their own experiment. So these computations and these experiments should be something that's repeatable, and someone should be able to recover all this from, well, so in our paper, everything is described, the cell complex and so on, and an expert in topology then could write their own code to compute homology of these configuration spaces. But we've also made our code publicly available on GitHub and so on, so that anyone else could you know, download our software and start playing around with it themselves if they wanted to do further experiments. So this recent project was one where really computation and experiments were at the heart of it, and I wouldn't say in this case that it helped us prove the theorems at all, but when we looked at the theorems that we had and the experiments that we'd done and tried to find kind of a unifying picture that explained everything we had seen so far, you know, it really informed our conjectures. And I think we got a much sort of sharper and more convincing picture of what's really happening just from the experiments. Loosely speaking, by a cell complex, I mean a shape or a topological space that you can build out of simple building blocks. So imagine something like Legos or Tinker Toys, where you can snap them together in all kinds of different ways, but there's only sort of so many ways you can snap them together. So imagine, for example, just you know, trying to make a surface, but the way that you're making the surface is by just gluing triangles together side by side. So that might be you know, a good example of a cell complex. But, you know, maybe your building blocks, your Legos, could be squares, or, you know, maybe something more complicated. But so in this case, it turns out that the cell complex that we have is a particularly nice one called a cubical complex, and all of the cells are cubes. So the one-dimensional cells are little line segments, and the two-dimensional cells are squares, and the three-dimensional cells are cubes, but then there's also higher dimensional cells, hypercubes. But what's nice is that we can say exactly how many cells there are of each type, each dimension, and how they're kind of glued together. So, and we can give it a very compact description. So, so you could, send an email to someone saying, here's my cell complex. Can you, compute the homology of it with your software? So we have a precise and compact description of what the cell complex is. So, but essentially, to answer your question, this is what a cell complex is. It can be a shape that's almost as complicated as you can imagine, but it's made out of simpler shapes. In our case, cubes that are just glued together. So that has some advantages, that it allows you a precise description, it allows you some computation, and it's the most important thing is that it's finite. So for example, like if you're a little ant living on a sphere, you could be anywhere on the sphere, so there's only finite area, but there's infinitely many points. You could be here or there or anywhere in between. It's sort of a continuous space. But if I want to describe that two-dimensional sphere that the ant lives on as a cell complex, then I would just take, maybe 4 triangles and glue them together like the way they're glued together in a tetrahedron, the 4 sides of a tetrahedron. So that, that's a shape with sharp edges and pointy corners, but to a topologist, it's exactly the same as a two-dimensional sphere, because topology is like rubber sheet geometry, and we can just deform one space to another, as long as we do it without ripping or making any new holes, anything like that. So, so another way to make a two-dimensional sphere as a cell complex would be to glue together 6 squares, like like a cube. And again, geometrically, there's corners and edges and so on, but topologically, topology doesn't see that. Topology just sees it like the same as it would see a two-dimensional sphere. So, but again, the advantage of a cell complex is you can just sort of write it down exactly, and that there's only finitely many cells. So you could encode it in a computer program. This is a great question, and I'm sure it's different for every mathematical researcher. I think something that many researchers have in common, though, and that might not be known to the general public, is how much the questions that we pursue are driven by aesthetics and just and curiosity. I think I've often been drawn to a certain question just because it seemed attractive, and I was curious about it. But as I've gone on in my career, and I think, maybe matured as a researcher a little bit, I think your tastes are influenced by other mathematicians' tastes, and you do think, well, not just what you would find interesting, but what the community would find interesting. And I do like problems like this, like what I've been talking about in terms of configuration spaces, because it's something that might even be of interest to the physics community. But I'm doing a lot of mentoring of graduate students these days, and I'm sort of always trying to find interesting things for them to think about. But I tell them that my style as an advisor is to suggest lots of problems, and my idea is not that they'll pursue all of them, but that they would pursue 1 or 2 of them. And what I want to find out as the advisor is what they're interested in and what they're good at. So by suggesting lots of problems, I just want to sort of see what captures their attention. And the truth is, research is very hard. And so I'm not sure how we could do it, how we could spend weeks or months or years being stumped by something and frustrated that we can't figure it out. if it wasn't something that we were also sort of, delighted by, that something that we found very interesting. Uh, I have to say I really enjoy spending time with my family, and I have a 2.5-year-old daughter now, and um, so this has been one of the good things about the pandemic, is getting to spend more time at home, spending more time with my family, and traveling less. So I have some other interests, or hobbies outside of mathematics. Uh, I would say one of my passions is music. I love listening to music and discovering new music to listen to, and and sometimes I sort of like to poke at the piano a little bit. So that's something that I find to be fun. Um, I like to play chess, and that's something that I hadn't done uh, for a long time, but lately I started playing chess a little bit just online. One other thing that I like to do on the chess websites is to try puzzles, and um, and then looking at the puzzles, it it almost reminds me sometimes of a math problem where there's the same satisfaction of figuring it out, that there's like a little aha moment in your brain where it clicks into place, and somehow in a chess problem, sometimes you see what the ideas are when you look at the position, that you want to get this piece here and this piece here, and you can kind of almost imagine what the final position should look like, but it's not clear how to get there because it's not clear what the right order to make the moves is. If you do the moves in the wrong order, then the opponent has a way out. So um, somehow that almost reminds me of a mathematical proof. Sometimes you need to do not only the right things in the proof, but you need to do them in the right order, where the problem gets away from you and your proof doesn't work. One other thing I've noticed is that I'm often stumped on a puzzle, uh, and just don't know what to do. And then I leave the room to go get a cup of coffee or go do something else. And when I come back and look at the puzzle, I have a fresh insight. Sometimes it clicks. And math is sometimes like that. We sometimes think that we're going to solve the problem if we just try harder, but I don't think that's always true. I think sometimes the best thing to do is uh, stop and um, put it away and come back to it. With math problems, I think sometimes days or weeks later, or there's some problems that I've tried on and off for years, and you come back a year or two later, and maybe you have some different ideas. Maybe some different mathematical techniques than you knew last time you looked at the problem, but maybe just your perspective is different and you have a fresh insight into it. So I think chess puzzles to me are like a little like kind of microcosm of that. The chess puzzles are much simpler than math research problems, and there's always an answer. At least the computer knows what the answer to the chess puzzle is. The computer can find the best move to that chess position, but it feels like it has some of those things in common, that there's a little satisfaction of solving it, doing the right things in the right order, and there's also some benefit to like looking away and going and doing something else, and then coming back and looking at it with fresh perspective. So it kind of reminds me of math problems. I sometimes, when I get on my computer in the morning, like to do a few chess puzzles just to sort of warm up my brain. I feel like just sit down and do something like that, where I have to think about it for a minute. I have to use my kind of critical mind, but it's not stressful, and it's somehow easy and satisfying sometimes to solve a few chess problems in a row. and mathematics is rarely that easy or satisfying. I feel like the insights in mathematics are much fewer and far between. We're very trained in our specialties, so it's hard to explain it to somebody who isn't similarly trained. So this is one thing that maybe sometimes makes me sad about mathematics, is that you may learn something beautiful, or you may have a small victory on a problem you've been thinking about for a while, but there's very few people who you can share that with. Really, the only other people who you share that moment with and who understand exactly what happened are other mathematicians who share that same training. And by the time you get into your area of specialty, that might be just a dozen people scattered around the world or something like that. But at the same time, it's a human endeavor, and we share our little victories and losses, and so I might tell my partner about it, just the experience that I figured something out today that I'd been stumped on for a long time, and she understands that excitement, that relief. So we share our experience in that way, just the human experience aspect of it. And also, she's an artist, my partner, and so we like to enjoy art together. And if I had some figures that I drew for a paper, for example, that I really liked, I might show those to her and talk a little bit about what it means. As far as my 2-year-old daughter goes, she's just learning to talk, and it's just delightful. It's so sweet being able to have conversations now, and she's interested in learning to count, and that's sort of her mathematical journey right now, and I love hearing her count, and so she can she might say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then she's 13, 11, 60, 90. At a certain point, she starts either making up numbers like 11, or bouncing around between other numbers she's heard. And I don't know, there's something about it that's very sweet and very funny. But it also, makes me kind of curious and appreciative about how we all learned how to do this. And it's kind of amazing, actually, to think about what it even means to count something. We can say those numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but what does it mean? And it's kind of amazing that it means something like abstract already, like 2 muffins, and then there versus like 2 pencils or 2 car keys. Like it's always 2. So there's some, abstract, maybe platonic, meaning of 2. And just, and we kind of got that when we were little kids. So we've never really thought very much about it, but just counting something, you say 1, 2, and you don't touch the same object more than once, just once here and once here. And then you're like 1, 2. There's some process there, and there's some meaning to say that there's 2 of this or 2 of that. But the 2 means something just kind of on its own, independent of whether it's this or that. so these are all sort of like, basic things that, philosophy or the meaning underpinning our language and our most fundamental mathematical ideas. Having a 2-year-old gives me an opportunity to kind of see that with fresh eyes and appreciate it in a new way. It really is amazing that we learn to walk and talk and count and do all these things when we're so little, that we don't really remember doing all those things, but somehow we did.